Hello, everybody. Now we're going to do Chapter 6, Section 2, Real Applications of Normal Distributions. The claim to fame of this section is that up until now, we've always had to look at normal distributions, standard normal distributions. But now we don't have to, because now our formula that we use for our z-score, x minus mu over rho. Remember, it's rounded to 2 decimal places. What this equation does, it takes our mean and deviation and all the x values to both sides of the mean and allows us to calculate the percent of the data to the left of each of those values of x. So this is what's really happening with this formula. Okay, so in the past, we had mu and some value of x. And so and the chart tells us the area. So it gives us the probability. The probability is what the area is. Now, using our formula, we can now, this is a standard. This is non-standard normal distribution. We're going to convert it to a standard normal distribution. It's still going to be a bell curve. It's just now, this one just matters wherever our mean is. I think. So what we're doing now, we're converting our mean to 0. And now we're going to be looking at specific z-scores to find the probability. All right, so that is our claim to fame, our goal in what we're trying to do here. And remember, whenever we deal with Greek letters, we deal with populations. Remember, critical values were at 2 standard deviations, the values at 2 standard deviations. But we use negative 1.96 and positive 196 to separate those, make it much more uniform. All right, so let's say that our area was negative 2.0, our z-score was negative 2.03. And the mean is in the middle. That equals 0. We go from non-standard to standard. So since it's negative, we know it's to the left. So it's negative 2.03 standard deviations to the left of the mean. To find out the area that's to the left of it, we'd go to our z-chart. On top here, we have 0.0, the number. That's all the way in the heart. And on the vertical column, we have a number, decimal, a number. So to find this, we would go all the way down till we get to negative 2.0. And it always starts off at 0.00, 0.01, 0.02. Since this one is 3, we go to 0.03. Now, where both of these overlap or where they intersect, that gives us the percent of data to the left of that X value or Z score that created that specific Z score. Because remember, it's Z equals X minus mu over standard deviation is over the rho. We're looking at that X, that specific X with these constant numbers gives us negative 2.03. Right, so that's what we'll be looking at, and we'll try to keep in mind. Procedure to find the area with non-standard distribution. Steps. Step 1. Draw a sketch of the curve, the bell curve. Remember, the mu's in the middle. Locate the Z value. You have to use that with this formula. The table will give you the area to the left of Z. So draw a curve first. The mu goes in the middle. Calculate our Z value. And this finds us the area to the left. So if you want the area to the right, so if you want this area, then subtract what you find, subtract the area of the Z value, which is to the left. Subtract that from 1. So this is the area. Let's call this A. So this is 1 minus A. So we have approximating probabilities with areas under a normal curve. So here's your Z value. Remember, the whole area under this curve has to be 1.0. All right, so let's say that this Z value gave us the area to the left of this is 0.8119. To find this area, take 1 minus 0.8119, and that'll give you 0.1881. That is that area to the right of it. All right, let's see what the examples say. Example 1. What proportion of men are taller than 72 inches? What proportion of men are taller than 72 inches? Okay, let's see what they give us here. What information? The heights of men are normally distributed with a mean, it says the mean, of 68.6 inches and a standard deviation of 2.8 inches. Find the percentage of men who are taller than the shower head positioned at 72 inches above the floor. Here's the mean. So the mean is 68.6. We're looking for taller than 72. So we got to find the area to the left and subtract it from 1. So the Z value, X minus mean over rho, X is 72 minus 68.6 over 2.8 equals 3.8 over 2.8, which is 1.21. So looking at our chart, we go down to 1.2, 0.01, and where they overlap, we get 0.8869. So that says the area to the left of it is 0.8869. What we have to do to find this is 1 minus 0.8869, and we get 0.1131. So it tells us that 11.31% of men are taller than 72 inches. That's what it tells us. All right, see what's next. Example 2. What's example 2 say? Okay, Air Force. What it says here, it says airport height requirement. Until recently, it says Air Force height requirement. Until recently, the U.S. Air Force required that pilots have a height between 64 inches and 77 inches. Heights for women are normally distributed with a mean at 63.7 inches and the standard deviation of 2.9 inches. What percent of women meet the height requirement? What percent of women meet this height requirement? Draw a graph. We know the mean is 63.7 inches. We want to know from 64 to 77. We want to know this area because that's going to tell us the probability that the women fit in that zone. So we have our z-scores. We have to find the z-value for the first one. We'll be using z x minus mean over rho. So x is 64 minus the mean, which is 63.7 over 2.9 equals 0.01. So the area of that part is 0.5398 from our chart. So that's this first part, 0.5398. Then we are looking for the second z value, which is 77 minus the 63.7 over 2.9, which is 4.59. And the area for that one is 0.9999. So that area is 0.9999. So taking this is A2, this is A1, taking A2 minus A1, we get 0.9999 minus 0.5398. That gives us 0.4601. Well, that tells us is 46% of women meet the U.S. Air Force height requirement. All right, let's see what else we got. No, we don't need that. We don't need that. All right, so this is procedures for finding values from known areas of probability. Procedure to find values from known areas or probabilities. So here's an example. So let's say the mean was 63.7 inches and the row is 2.9 inches. I can ask you the question, what height would a woman need to be taller than 40% of other women? Using the same information. So the average height of women is 63.7, the standard deviation is 2.9. So the first step we have to do is the graph. We have our mean in the middle, that's 63.7. Remember, that's at 50%. So I want to know what is that X value where it's bigger than 40%. So the second step, Z is equal to our formula, X minus over rho. We're looking for X. So first thing we do, multiply both sides by rho. So I have Z times rho was X minus mu. We're solving for X, so we get rid of the mu by adding mu to both sides. So Z times rho plus mu equals X. So this is our formula. We calculated our Z. No, we didn't calculate it. That's what we have to do. We know the rho. The rho is 2.9 plus 63.7. So now we got to find our Z. We know the Z because according to our table, we want it to be bigger than 40% of the data. So what we have to do here is somewhere in this table, find 0.400. If it's between two numbers, always go to the one that's it's closer to. If it's exactly in between two numbers, then add the two of them and divide by 2. So say if it was between 0.02 and 0.03, then between there would be 0.025. So if we look in our table, this number goes to 0.2, and up here it's 0.05. So it's 0.025, or 0.05, I mean. But since it's to the left of the mean, it's got to be a negative 0.25 times 2.9 plus 63.7 equals 62.97 inches. So what we would do is roughly around 63 inches. Okie doke. Let's look at example 3. There's example 3? Designing front door of a home. Designing front door for a home. It says, when designing equipment, one common criterion is to use a design that accommodates at least 95% of the population. With what is the height? So we're going to use at least 95% of the population. What is the height of the door that would allow 95% of the adults to walk through the doorway without bending or hitting their heads? Assume the heights of adults are normally distributed with a mean of 66.2 inches and a standard deviation of 3.8 inches. It's asking, how does the result compare to the height of 80 inches? How does this height compare to the 80 inches required by code? So first step is draw the graph. Means in the middle, and we know the mean is 66.2 inches. What we want our doorway to be at least 95% of the population. So we have to find what number is 95% of the population. That's going to give us this value. So that's what we have to look for is in our Z table, look for whatever is closest to 0.9500. 1.6, 0.05. So because of that, our Z value is 1.65. Now we know the Z value. We know the mean and deviation. Let's find X, how tall the door is. So plug in our formula. X minus mu over rho. Z is 1.65. We don't know what X is. Minus 66.2. 3.8. Solve for X. First thing we gotta do is get rid of the denominator. So multiply both sides by 3.8. So we have 3.8 times 1.65 equals X minus 66.2. Add 66.2 to both sides. So we have, well, because we're looking for X, we say X is equal to this whole thing. So it's 3.8, 1.65 plus 66.2. That is 72.47 inches, which we're rounded up to be 80 or 73 inches. Well, that's pretty close because if they're saying 80 inches and we have 73, yeah, then we will have more than 95% of the men walk through without hitting their heads. Let's see some next example. Yeah, so it's a good number. The question that I was asked is how do we get that? So how do we calculate how to solve for X with this formula? It's a process of opposites. What we have to do, since we're looking for X, remember the order of operations always do special operations first, square roots, absolute values, all sort of stuff. Then you do multiplication and division. And then lastly, you do addition and subtraction. But because there's another rule that helps solve these things, whenever you have fractions and an equal sign, whenever you have fractions and equal sign, get rid of the fraction. Find the least common denominator. So in this case, the only denominator we have is rho. Multiply each term by the LCD. When we say term, it's anything separated by plus, minus, or equals. No, this is important. This is an equation, so it has to stay together. So we only have two terms. So our LCD is rho. Multiply rho on this side and rho on that side. Reduce or cancel, because this will get rid of the denominators. So we have x minus mu. Multiply to remove parentheses. But since these canceled, there's nothing to multiply. It just drops them. And then solve for x. We're going to get x by itself. So what's the opposite? Since this is division, the opposite of division is multiplication. This is subtraction. The opposite of subtraction is addition. Whatever you do to one side, you have to do to the other. So we have rho times z plus mu equals x. So that's how we solve for x. Now let's talk about significance. When we talk about significance, we've done this all along. That's our plus or minus 2 rho. So it's plus or minus 2 rho. So minus 2 standard deviations plus 2 standard deviations from our mean. Remember, we have this number here is our critical value. It's mean minus 2 standard deviations. And this is our critical value on the other side, mu plus 2 rho. So anything to the left of this is significantly low. Anything to the right of this number here is significantly high. So now in these type of experiments or the calculations, if we don't really have the rho and standard deviation, we have a standard common values we always use. Remember last time we used negative 1.96 and positive 1.96 because what that was 0.25 on both sides. But now in this type, we have the probability of x or greater is less than 0.05. That if a number is x or greater and it's in the range of 0.05, the outer edge, this part here. If it's significantly low, we can say that if x is or lower, and that probability is less than 0.05. So if the probabilities are less than 0.05, then that's significantly low. or significantly high. So it's a probability. These probabilities are very small. Why? Because they're on the very outside of our uh, what do you call it? Our curves. Let's look at example 4. What is example 4? Where's there it is on the bottom. Example 4 is significantly low birth weight. Okay, what this is asking us is this. Use the preceding criteria to identify significantly low birth weights in grams of males based on our data. What we're looking for is significantly low birth weights of male babies. So according to male babies, they're normally distributed, and they have the mean birth weight of 3272 grams and the standard deviation of 660.2 grams. We're trying to find significantly low. So what are we looking for here? Use preceding significantly based on the data. Assume is that. Oh, okay. So we're going to find what value. So what we're looking here, our picture. Our means right here. Significantly low. That's this. What area is that? The area there is 0.05 because of what we just said here. If it's significantly low, the probability of that X value or lower is less than that number. So we're looking for is what number would be bigger than 0.05% of our data. And this, the mean is 3272 grams. And the deviation is 660. So using our formula, X minus mu over rho plug in what we know. We're solving for X. Our Z is 0.05. The mu is 3272 grams over 660.2. Nope, we know. This is the area. We need the Z-score. So we have to find out what is 0.05. Now, in our chart, this number falls exactly between 0.04 and 0.05. It's negative 1.6 is to the left. Since this number falls exactly between these two values, we take negative 1.64 plus negative 1.65, add those together, divide by 2, we get negative 1.645. That's the Z value we'll be using because it's exactly in the middle of the two. So we have negative 1.645 x minus 3272 over 660.2. First step is get rid of the denominator. So multiply 660.2 to both sides. So we have 660.2 times negative 1.645 equals x minus 3272. Then we add 3272 to both sides. Those cancel, so x, which is right there, x is equal to 660.2 times negative 1.645 plus 3272. Plugging all that in, we get 2186.77 2186.8 grams. So that's the probability of the birth being less than 2.186. All right. And that's it. Well, everybody, thank you much.